There is a particular kind of engineering problem that doesn't get enough attention in the world of infrastructure mega projects. It is not the problem of building something enormous in an empty space, which is difficult, but straightforward in the way that most large challenges are straightforward. You have room to work, room to make mistakes, room to sequence construction without everything colliding with everything else. The more interesting problem, and the more brutal one, is building something enormous when there is essentially no room left. When the site is already full. When the operations you are trying to expand are happening simultaneously in the same physical space where you are trying to build the expansion. When stopping is not an option, and neither is moving outward. That is the specific engineering reality facing Seattle-Tacoma International Airport right now. Sea-Tac, as it is universally known, sits on a narrow ridge between two valleys in the southern suburbs of Seattle, hemmed in on every side by Interstate 5, state highways, the city of Sea-Tac, and decades of urban development that have left the airport with essentially no meaningful room to grow horizontally. The airport cannot expand its footprint in any conventional sense. The land simply is not there. And yet Sea-Tac is one of the fastest-growing major airports in the United States. Passenger volumes have been climbing for years, driven by the extraordinary growth of the Seattle metropolitan area, the dominance of Alaska Airlines as a hub carrier, the significant Amazon-driven cargo operations that flow through the airport, and the general expansion of air travel demand in the Pacific Northwest. The airport that was built for a certain volume of passengers is now handling substantially more, with substantially more projected to arrive over the next decade. The solution Seattle-Tacoma International has committed to is $5 billion worth of compressed, vertical, innovative engineering, building upward, building over, building inward, doing more with a footprint that cannot meaningfully grow. And the centerpiece of that effort is one of the most genuinely remarkable pieces of airport infrastructure built anywhere in the United States in recent years. The International Arrivals Facility and its associated aerial walkway represent the most visually dramatic and engineering-intensive component of the Sea-Tac expansion program, and understanding what was actually built here requires appreciating just how constrained the problem was from the beginning. International arriving passengers at any major airport face a specific processing requirement. They must pass through customs and immigration inspection before entering the public areas of the terminal. At most airports, this means arriving passengers travel from their gate through internal building corridors to a customs hall located within the terminal structure. At Sea-Tac, this was always complicated by the airport's physical layout. The international gates on Concourse A were located at a significant distance from the customs processing facilities, and the path connecting them ran through areas that were already congested and increasingly inadequate for the volume of international passengers the airport was handling. The conventional solution, building new customs facilities closer to the international gates, or expanding the existing facility through internal terminal modifications, ran directly into the airport's fundamental space constraint. There was not sufficient room within the existing building envelope to create the customs processing capacity the airport needed at the scale it needed it. Something more creative was required. What was designed and built is an entirely new international arrivals facility, a dedicated building for customs and immigration processing that is physically separate from the main terminal structure. The IAF sits on the eastern edge of the airfield, positioned to receive international passengers from the gates that handle those flights, and connecting the IAF to those gates, spanning above the active taxiway system of one of the busiest airports on the West Coast, is an elevated pedestrian bridge that rises approximately 85 feet above the airfield surface. Let that physical reality settle for a moment. Passengers walking through this structure are traveling at roughly 8 stories of elevation in an enclosed walkway, directly above commercial aircraft that are actively taxiing beneath them. Wide-body international jets, aircraft that may be 200 feet long and 60 feet tall, are moving underneath while passengers are walking above. The engineering required to make this safe, structurally sound, and capable of handling thousands of passengers per day without interfering with the airfield operations below is extraordinary. The foundation system for the bridge had to be designed and installed on an active airfield, meaning construction crews were working in the operational environment of the airport, subject to all the restrictions, scheduling constraints, and safety protocols that entails. The structural elements had to be positioned and erected without impeding taxiway access or flight operations. The timeline for each phase of foundation and structural work had to be coordinated with airfield operations to ensure that aircraft movement was not disrupted, and the finished structure had to meet not just conventional building code requirements, but the specific and demanding safety standards that apply to any structure in proximity to active aircraft operations. The International Arrivals Facility itself, at its destination end of the bridge, significantly expands Sea-Tac's capacity to process international passengers. New customs and immigration processing lanes, modern Federal Inspection Service facilities, and a baggage reclaim area designed for the volume of international arrivals the airport is now handling. All of this is housed in a building that simply could not have been accommodated within the existing terminal structure. The IAF represents a genuine capacity unlock for Sea-Tac's international operations, and it does so through a solution that would simply not have been possible at most other airports, where the airfield geometry and surrounding infrastructure would not permit an elevated crossing of this nature. While the International Arrivals Facility and its aerial walkway are the most spectacular component of the Sea-Tac expansion, they are not the only significant work underway as part of the Sustainable Airport Master Plan. Throughout the terminal and concourse system, a parallel set of projects is attacking the airport's capacity constraints from a different angle, not by building new structures over the airfield, but by extracting more efficiency and more passenger handling capacity from the existing building footprint through vertical expansion and interior reconfiguration. Concourse C, which handles a significant portion of Sea-Tac's domestic traffic and sits at the core of the airport's operational flow, is the primary focus of the terminal extension work. The concourse is being expanded vertically and reconfigured internally to increase the number of gates it can accommodate and improve the passenger experience within its constraints. This kind of expansion, adding height and interior capacity to an existing structure rather than pushing its footprint outward, is inherently more complex than horizontal expansion would be. Structural modifications to an existing building require working around and within the building's existing skeleton, maintaining the integrity of the structure throughout the construction process, and sequencing the work so that portions of the concourse remain operational while adjacent sections are being rebuilt. The gate additions resulting from this work represent meaningful capacity growth for an airport, where every additional gate translates directly into additional revenue, additional passenger throughput, and additional resilience in the scheduling system. At an airport as constrained as Sea-Tac, a handful of new gates is not a marginal improvement. It is a significant operational gain that affects the airport's ability to attract new routes, accommodate airline growth, and manage the inevitable disruptions that come with operating at or near capacity on a daily basis. The ticketing and check-in areas of the main terminal are also being modernized as part of the SAMP program. The check-in experience at Sea-Tac, like that at many airports built in an earlier era of commercial aviation, was designed around assumptions about how passengers interact with airlines that no longer hold. The prevalence of mobile boarding passes, automated check-in kiosks, self-service bag drop systems, and the general shift toward passengers arriving at the airport with much of their processing already complete, has changed what an efficient check-in area actually needs to look like. The modernization work at Sea-Tac is reconfiguring the space to reflect these behavioral realities, reducing the footprint dedicated to traditional staffed counters and expanding the automated and self-service infrastructure that contemporary travelers prefer and that processes higher volumes more efficiently. Woven throughout the Sea-Tac expansion program is a sustainability framework that distinguishes this project from many comparable airport expansion efforts and reflects both the environmental values of the Pacific Northwest and the economic logic of long-term infrastructure investment. The Sustainable Airport Master Plan is not called that arbitrarily. The environmental performance commitments embedded in the project include targets for carbon reduction in building operations, integration of electric ground support equipment infrastructure to support the transition away from fossil fuel-powered airfield vehicles, advanced building systems designed to reduce energy consumption relative to conventional airport construction, and water management systems appropriate to the Pacific Northwest environment. The baggage handling systems being installed as part of the expansion incorporate automation technology that reduces energy consumption while improving the speed and accuracy of bag routing, a combination that serves both the sustainability agenda and the operational performance goals of the airport. These commitments are not purely altruistic. There is a straightforward business case for building sustainable infrastructure in a market where the major airlines operating at the airport have made their own environmental commitments, where the regulatory environment is moving consistently in the direction of stricter emission standards, and where the long-term operating costs of energy-efficient buildings are meaningfully lower than those of conventional construction. SEATTLE-TACOMA International is building for a 50-year horizon, and the sustainability investments embedded in the SAMP program are partly bets on the future operating environment that the airport expects to inhabit over that horizon. But the honest story of the Sea-Tac expansion cannot be told only through the lens of engineering achievement and sustainability vision. Because executing a $5 billion construction program inside an airport that is already operating at the edge of its physical capacity creates pressures and risks that deserve direct examination. The cost trajectory of the program is perhaps the most immediate concern. The $5 billion figure that defines the SAMP publicly is a planning estimate derived from projections made during the program's design phase. Large construction projects in constrained operational environments have a well-documented tendency to encounter costs that exceed their initial estimates, driven by factors including construction complexity, schedule disruptions caused by operational requirements, supply chain volatility, and the inflation in materials and labor costs that has characterized the construction industry in recent years. At Sea-Tac, the specific conditions of the site amplify these risks, working on an active airfield, building structures over live taxiways, sequencing construction around the operational needs of an airport that cannot meaningfully reduce its activity to accommodate the construction. All of these conditions add cost and complexity that standard cost models do not fully capture. Financial analysts and infrastructure watchdogs tracking the SAMP program have expressed concern that the final accounting of the project's costs, when all phases are complete, will exceed the $5 billion figure by a margin that the airport and the Port of Seattle will need to explain to the public. The mechanism by which cost overruns at an airport ultimately affect travelers is the same one that operates at every major airport in the United States. The Port of Seattle, which operates Sea-Tac, finances capital investments through a combination of bonds, federal grants, and the fees it charges airlines for using airport facilities. Those fees are a component of the cost structure that airlines factor into their pricing models. When airport fees rise to service higher debt loads created by cost overruns, the pressure flows downstream through the airline cost structure, and eventually, in some form, into the ticket prices that passengers pay. The transmission is not always direct or transparent, but the economic logic is consistent. The operational pressures of building inside an active, constrained airport are felt most acutely during the periods when passenger volumes are highest. For Sea-Tac, those periods are well-defined and entirely predictable. The Thanksgiving travel rush in late November, the Christmas and New Year holiday travel period, and the peak summer travel months when leisure travel demand surges across the Pacific Northwest. During these periods, the airport operates at and sometimes beyond its comfortable capacity. Security checkpoint queues extend further than they should. Gate areas fill beyond their designed passenger loads. Baggage systems strain under volume that approaches or exceeds their rated throughput. And into this already stressed operational environment, the active construction program introduces additional constraints: modified passenger flow paths around construction areas, reduced availability of certain amenities and services, and the general friction that comes with navigating a major public building that is simultaneously under construction and fully operational. Aviation experts who study airport operational performance during construction periods have noted that the risk of significant passenger experience degradation during peak travel periods is real and not fully mitigable through planning alone. Construction walls that redirect passenger flow create longer walking distances and more confusing wayfinding. Reduced availability of food and retail services in construction zones creates pressure on the remaining open concessions. And any construction-related incident, a delay in a scheduled work phase, an unexpected infrastructure issue, a supply chain disruption affecting a critical material, can cascade into operational impact in ways that the construction schedule does not always account for. Sea-Tac's leadership and the Port of Seattle have emphasized their commitment to managing construction phasing in ways that minimize peak period impact. But the history of large airport construction programs, including several discussed elsewhere in this series, suggests that the gap between planning intentions and operational reality during peak periods is almost always wider than anyone anticipated at the outset. And then there is the question that sits at the very end of the $5 billion investment, the question that no one involved in delivering the SAMP particularly wants to answer publicly, but that the data makes difficult to avoid. Will it be enough? Sea-Tac's passenger growth trajectory, if it continues at rates consistent with recent years and with the economic projections for the Seattle metropolitan area, will push the airport toward its absolute physical capacity within a time frame that some industry analysts describe as a single decade beyond the completion of the SAMP program. The expansion being built now is designed to accommodate a certain volume of passengers. That volume will, if current trends persist, be reached and exceeded by the mid-2030s. At that point, the options available to Washington state aviation planners will be severely limited by the same constraints that have defined the Sea-Tac expansion program from the beginning. The airport cannot expand horizontally. The surrounding urban environment has not changed. The alternatives: a second major airport somewhere in the Puget Sound region, a more aggressive development of Payne Field in Everett as a relief airport, a fundamental rethinking of how aviation capacity is structured across the Pacific Northwest, are politically, financially, and logistically complex in ways that make them very difficult to advance. The SAMP program is not ignorant of this reality. The sustainability in the plan's name refers partly to a philosophy of building infrastructure that maximizes efficiency and extends useful capacity as long as possible within a constrained footprint. But efficiency has limits. Vertical expansion has limits. Automated baggage systems and self-service check-in and optimized gate configurations can squeeze meaningful additional capacity from a fixed site. But they cannot substitute indefinitely for physical space that simply does not exist. Seattle is one of the most economically dynamic metropolitan areas in the United States. It is home to major global technology companies, a significant international trade relationship with the Pacific Rim, and a population that is growing at rates that consistently exceed national averages. The aviation infrastructure serving this region is going to face demands that no single $5 billion program, however intelligently executed, can fully accommodate over the long arc of the coming decades. What Sea-Tac's $5 billion master plan actually represents, in the most honest assessment, is the best available answer to an extremely difficult question. How do you serve a growing city from an airport that cannot grow? The answer is the International Arrivals Facility, rising 85 feet above live aircraft. The answer is Concourse C, being rebuilt vertically to extract every available gate from a footprint that cannot move outward. The answer is sustainable building systems and automated infrastructure and intelligent space design that together push the capacity ceiling of a constrained site as high as physics and engineering will allow. It is an impressive answer. It is also, almost certainly, a temporary one. Temporary in the way that infrastructure investments often are when they are applied to sites whose fundamental constraints cannot be engineered away. Seattle will eventually need to have a harder conversation about the long-term future of aviation capacity in the Pacific Northwest. The SAMP program buys time for that conversation, builds quality into the interim, and demonstrates that serious engineering ambition can extract remarkable results from the most unpromising spaces. But the clock that the $5 billion starts is not a long one, and when it runs out, Washington State will need answers that no amount of vertical expansion, however brilliantly executed, can provide on its own. Drop a comment below and tell us what you think. Can Sea-Tac survive the next decade on this plan alone? Or is it time for Washington State to start building a completely new airport from scratch? Subscribe to Mega Airport Works and stay with us as we track the biggest and most consequential mega projects on Earth.